Hello everyone, I took this picture landing in São Paulo, Brazil. It shows the immensity of buildings that we have in the city. The work I'm going to show you today is about the impact of build density and surface materials on urban microclimate for São Paulo, Brazil, through the simulation of different scenarios using unmet full forcing tool. My name is Carolina Gusson. I am an architect and urban planner and a PhD from the School of Architecture and Urbanism for the University of São Paulo, Brazil. First, I would like to show you why we are interested in studying this topic. Then, I will show you how we did the study, the field campaign, the calibration, and the scenario simulations. Then, the results, and finally, the conclusions. This research has two approaches: measurement and simulation, and how to combine them to achieve more accurate results. In recent years, urbanization has been particularly great in tropical climates and is likely to even increase. The climatic problems in Brazil cities today are showcased to other developing urban areas in tropical climates. São Paulo is the fourth urbanized region in the world with the largest population, of around 21 million inhabitants, and it's characterized by a humid subtropical climate. São Paulo urban area is very heterogeneous, so it's important to do measurements and model calibration in the study interest area before going to parametric simulations. A field campaign was undertaken in the 2 points of the most densely built area of the city. The variables collected were air temperature, relative air humidity, wind speed, wind direction, and gray globe temperature. The measurements were taken from April 15th to April 25th, 2016. April 2016 covered significantly more days with maximum temperature above 30 degrees than the long-term average. The variables required for the full forcing tool are direct and diffuse short-wave radiation, long-wave radiation, air temperature and humidity, wind speed, and direction. The simulation input data were from April 16th to April 18th, considering that April 17 had no occurrence of clouds, resulting in a 48-hour simulation. The input data for air temperature and relative humidity were obtained from the average values measured at the 2 points. The direct and diffuse shortwave radiation and long-wave radiation were recorded by a fixed platform on the top of a building. As the wind speed in the measurement area is very low, it was decided to maintain the input wind speed and direction constant. The simulation took 12 days. 15 different parametric scenarios were generated combining 3 different height of towers blocks with 5 different surface building components. The building scenarios increase in height and maintain similar plot ratio by decreasing the site coverage. All the 3 building scenarios should have a plot rate like the field campaign areas. The building components are the concrete hollow block, the ceramic hollow brick, and the laminated glass. The surface finishes are composed of 2 extreme values of albedo. 0.02 represents a black surface and 0.9 as a white one. And for laminated glass, one more heat reflective and another more heat transmissive. Its simulation took 3 days. Air temperature behaved practically the same. The measured temperature was slightly higher at noon than the simulated one. MRT followed the curve of the measured data, but always slightly below it. The R-square for air temperature and MRT show very high correlation. RMSE values of MRT are higher, which is mainly caused by greater difference at nighttime. For the results, we'll consider the values of mean radiant temperature and temperature of equivalent perception. Outdoor in the pedestrian level at 12 p.m. TEP is a thermal index developed for local conditions. The 81-meter high scenarios and the east-to-west axis present the best results due to the shading effect. Average difference is around 11.6 Kelvin for MRT between axes and 2.5 Kelvin for MRT between height. At night, the building geometry had a small influence on MRT and TEP because their close ranges of build volume and plot radius. Consider building surface components and finish behavior for 12 pm. Transmissive laminated glass had a lower MRT and TAP values, whereas the white concrete hollow block resulted in higher values with average increase of 8.1 Kelvin in MRT over the laminate transmissive glass. At night, the highest MRT and TEP were found on the concrete hollow block with a black finish, with an average increase of 3.9 Kelvin in the MRT compared to transmissive laminated glass. MRT and TEP are higher in scenarios with components that store more heat. It's important to seek compatibility to the best thermal performance between day-night and interior-exterior. AVMAT presents good statistical results in calibration despite underestimating the MRT at night. The combination effect of geometry, building components, and surface finishes generates a daytime difference between the scenarios up to 22.1 Kelvin in MRT and 11.9 Kelvin in TEP. During nighttime, differences were of at least 4.1 in Kelvin in MRT and 2.7 Kelvin in TEP. Site coverage and height were the dominant factors that most influenced the microclimate during daytime, improving shade and ventilation. In the daytime, the surface finish influenced both the inside and the outside of building. The reflective finish causes discomfort for pedestrians in open space, but it can improve conditions in indoor space, whereas darker finish improves conditions in open space, but can contribute to the air temperature increase inside the building. The building components have a great impact on the nighttime thermal comfort in the urban environment due to their heat storage properties. The next steps will discuss the relationship between the results active and the build density of subtropical cities regarding geometry and build facades. I'd like to thank you for your attention and please keep in touch.